Hey everyone, have you ever just stared at a periodic table and thought, why are these numbers so weird and specific? Well, today we're going to pull back the curtain on two of the biggest ideas in chemistry: how in the world we actually weigh a single atom, and then how we count them when there are literally trillions of them in a single speck of dust. And believe me, it's a lot more straightforward than you might think. So yeah, let's kick things off with that big mystery. I mean, think about it. Atoms are made of protons and neutrons, right? You can't have half a proton. So why does the periodic table give us these funky decimal numbers for atomic mass? Like carbon isn't 12, it's 12.011. What's the deal with that? That is the very first puzzle we are going to solve together. Okay, so here's our game plan. We're essentially going to build two bridges in our minds today. The first bridge is all about figuring out the mass of one single average atom. And the second bridge, that's going to connect that impossibly tiny atomic world to the world we live in, the one where we can actually weigh things out in a lab. Right. Let's get into part one, weighing the unweighable. Here's the thing you have to get your head around first. Not all atoms of an element are created equal. They actually come in slightly different versions. So to get that one number you see on the periodic table, we have to figure out a special kind of average. Before we even think about chemistry, let's make this super simple with an analogy. Picture a giant box of paper clips. Now, most of them, let's say 75%, are just your standard 1-gram paper clips. But the other 25% are these heavy-duty ones that weigh 5 grams. So what's the average weight? You can't just do 1 plus 5 and divide by 2, right? Because they're not 50-50. We need what's called a weighted average. Let's look at how that works. You take the portion of the regular clips, 0.75, and multiply it by their weight. That gives you 0.75. Then you do the same thing for the heavy ones, 0.25 times their weight, which is 1.25. Add those two numbers together, and you get 2.0 grams. And notice something important. The average, 2.0, is way closer to 1 than it is to 5. And that makes perfect sense because the 1-gram clips are just so much more common. And boom, that brings us right back to chemistry. Those different paper clips, they're basically just like isotopes. You can think of isotopes as different flavors of an element. They're all atoms of the same element. They have the exact same number of protons, which is what defines the element, but they have a different number of neutrons. And those extra or fewer neutrons change their mass, just like our regular and heavy-duty paper clips. And look at this. It's the exact same problem. On the left are paper clips. On the right, some made-up element we're calling setlium. Just like with the paper clips, we've got two versions, two isotopes, and each one has its own specific mass and its own natural abundance, or how common it is. The way we're going to find the average atomic mass is, you guessed it, identical. So let's just follow the recipe. First, turn those percentages into decimals. Then we multiply the mass of isotope A by its abundance, 0.32. Do the exact same thing for isotope B. Then we just add those two results together. We get 43.77 atomic mass units, or AMU for short. That's the unit we use for atoms. And that number, that weighted average, is what you would see for our fictional element, cellium, on the periodic table. Simple as that. Okay, so that was our first bridge. We now know how to figure out the mass of a single average atom. But here's the catch. That mass is in AMU, a unit so ridiculously small that we could never, ever hope to measure it directly. So how do we get from there to grams? Something we can actually weigh on a scale? Well, the answer is this amazing little concept called the mole. Now, don't get weirded out by the name. A mole is really just a word that stands for a specific number of things, kind of like how a dozen always means 12. You could say the mole's the chemist's dozen, and it's our second and honestly our most important bridge. It's the thing that connects the tiny world of atoms to our big world of grams. And what is that specific number? It's Avogadro's number, and it is absolutely enormous. It's 6.022 times 10 to the 23rd power. That's a 6 followed by 23 zeros. To put that in perspective, if you had a mole of basketballs, you could create a new planet the size of Earth. It is a truly mind-bending number, but it is the key that unlocks everything else. And right here, this is the magic trick. This is the big aha moment. The reason the mole is so unbelievably useful is because that number on the periodic table, the one we just figured out how to calculate, it does double duty. For an element like phosphorus, that 30.97 is the mass of one average atom in AMU, and it's also the mass of 1 mole of phosphorus atoms in grams. The number stays the same, it's just the scale that changes. That's our bridge. Okay, Time to actually use this thing. Let's try a problem. Let's say we're in a lab and we weigh out 4.60 grams of pure silicon. The question is, how many moles of silicon atoms do we actually have in that little pile? All we need is our sample's weight and the atomic mass of silicon from the periodic table. Here's how it's done. You always start with the number you're given, the 4.60 grams. Then, we're going to use the molar mass from the periodic table to build a fraction. The key here is to set it up so the units you don't want cancel out. Since we want to get rid of grams, we put the 28.086 grams part on the bottom of the fraction. The grams cancel out, leaving us with moles on top. You run the numbers, and you get about 0.164 moles of silicon. All right, you ready to level up? Let's go one step further and cross both of our bridges in one go. Let's imagine we have a tiny, tiny speck of lead that weighs just 1/1000th of a gram. The ultimate question, how many individual lead atoms are in that speck? This is going to be a two-step calculation. So what we do is we just chain the conversions together. First, we cross that grams to moles bridge, just like we did for silicon, but this time using lead's molar mass. That gives us a tiny number of moles. Then, without even stopping, we use our second bridge, Avogadro's number, to turn that number of moles into an actual count of atoms. And just look at that result. Even in 1/1000th of a gram, you're still looking at almost 3 trillion atoms. Wow. And there you have it. It's really just those two ideas. We built one bridge to make sense of the average mass of an atom using isotopes, and then we built a second, super powerful bridge, the mole, to scale that up from the atomic level to the grams we can actually measure. With these two concepts, you can literally count the atoms in just about anything. A rock, a glass of water, anything. Which is a pretty incredible power when you think about it. And it kind of makes you wonder, what else is out there that we can learn to count, even when we can't possibly see it?